Good afternoon.
Good afternoon, John.
And welcome to this installment of the Back to Basics track. We're going to talk about object-oriented programming. And we're going to go directly to the elephant in the room, which is that object-oriented programming is not what the cool kids are doing in C++. And in fact, I proposed the same talk to another big conference, a conference that's run by a friend of mine, and it was rejected. And I wasn't really surprised by that, because what's the cool kids doing in C++ today? They're doing things at compile time, they're doing functional programming. They're cutting the edge of all that stuff. And this object-oriented programming stuff, this is so 90s, right? We already know all the best practices of that. We learned that in the 90s and in the aughts, and we've published that. This is all old news. But the problem with this is that in my role, and I'm a trainer, I go to companies and I try to take C++ programmers that are here and move them up here. That's what I do. And one of the things that I found is that although the cool kids aren't talking about object-oriented programming at conferences, the truth is that most programmers are doing object-oriented programming. Usually it's because of some legacy app, but often it's because they don't know anything about except object-oriented programming. That's what they know. And that's what they know, and because of legacy, their app is done that way, that's what they do. And the problem with this is that although we figured out these best practices a long time ago, they are not obvious. They need to be documented and explained, and no one's talking about them. Object-oriented programming is not easy. You can get it wrong a lot of ways. And the cool kids aren't talking about it at conferences, so we aren't cranking out new YouTube videos. So what we have is literally millions of people in the world that are doing object-oriented programming with no one telling them what the best practices are. Now we have books, I'm going to talk about some of them, that tell us best practices for object-oriented programming, but the problem is they were published so long ago, they're not modern. So nobody recommends them. Oh, go read the modern one. It'll tell you how to do lambdas, and it'll tell you how to do things at compile time. Well, that's all wonderful, but if you want to get best practices on object-oriented programming, there's not a lot of places that's happening, and I thought it should be, and so I have a little bit of influence on the program here. So you guys are going to hear my ideas about best practices. So we're going to talk a little bit about the theory of object-oriented programming, and then I'm going to do design guidelines and build guidelines. And I want to say, starting right up, we've got an hour. Actually, it looks like we have 57 minutes left. And in 57 minutes, we're not going to get everything. And I'm assuring you that I could spend a week talking to you about object-oriented programming. We would get a lot more background about the things that I'm talking about. We'd have a lot more guidelines than what I'm going to talk about, and it would give me more background, more applications. But we're going to have to do the highlight because we've got 56 minutes left. So let's talk about what I'm going to call the definition of object-oriented programming. And you're going to see that this is not the real definition of object-oriented programming. This is the definition we're going to use for this hour, because you can do object-oriented programming in Python, and I'm not going to talk about that. So my definition for the purpose of this talk is, it is a programming paradigm in C++ using polymorphism based on runtime function dispatch using virtual functions. So that's what we're going to talk about. The other thing I want to say is that there certainly are alternatives. I've mentioned a few already. Functional programming, object-based programming. We are not going to talk about why you'd want to use object-oriented programming or what might be better or what might be worse. I'm not here to defend object-oriented programming. When I told my wife that I was doing an object-oriented programming talk, she said, "John, do you really want to be the object-oriented programming guy? You want to be the guy from the 90s? I said, somebody needs to do it, and I guess it's going to be me. The other thing I want to say is that we're taking that you're doing object-oriented programming. We're taking that for granted, and now we want to do it right. Let's get best practices for doing object-oriented programming right. That's what this talk is for. We're also not going to argue about East const, West const type using any of that stuff. We're going to focus on object-oriented programming best practices. So object-oriented programming can be thought of in this way, and that is that derived objects are actually independent libraries that all happen to have the same API. And they do different things. The things they might do might depend on, the behavior could be something that's encoded at compile time. It's the code you wrote. But it might actually change based on the state of the individual object. So it's something you change at runtime. So that's a way of conceiving, thinking about object-oriented programming. So I'm going to give you a particular example, and this is as simple an example as I could come up with. So it's really trivial, but we're going to use it as our example today, and that is logging. And one of the nice things about object-oriented programming is, it gives us a separation of concerns. And in this case, what we have is we have application code, client code, that doesn't know anything about how logging will be done or what we're going to do with logs or any of that. What it knows is when something happens in the application that is worthy of logging. We have either done some event has happened, or we've entered some state or something that might be of interest from a logging point of view, so we're going to log it. But we don't know how it's logged. It could be sent to a server, it could be put on the console, it could be put to a file. That's unimportant. That's a different concern. That concern is in the derived class. And what ties the derived class with all these different implementations to the application is this commonality that is defined by the base class. The base class says this is the API. This is the constraint that the client has to call through. I use this API as a client. The application is going to use that API, and the derived classes have to derive from that API, and it's all going to work. I'm going to be able to change out the derived classes at will, and it's all going to work because of this tying API defined by the base class. So here is our base class. It's called logger, and it has a virtual function called log message. We could do a lot of different signatures here. We could use an std string. We could use string view. There's all sorts of things, but this is what we're doing, and this decision that's made by the base class is something that both clients and derived classes are going to have to live with. And we have an example, derived class. This is our console logger. It takes the log message, it logs it to the console. As I said, as simple as we can imagine. So the base class defines the library interface, and then you can have one or more implementations of that as long as they implement that API. So here's what client code might look like. We're going to refine this, improve it in just a minute. But in this case, what we have is we've created a console logger object, but notice it gets defined to a pointer to logger. And this is the pattern in object-oriented programming. This is what we have everywhere. The idea is you have some derived object, an object of a derived class, but it is referenced by either a base class reference or a base class pointer. That is what object-oriented programming is all about. So we have a compile time or a static type, which is the base class pointer, but it is not, in fact, actually that. The real object is a derived object. This is the pattern all the way through. We need to understand that. And the other thing to understand is that if we didn't have the virtual function call, that when we call this base class, it would the compiler looking at this and saying, oh, you're calling log message on what? On a pointer to a logger, so I'm going to look for logger log message. The only reason that we get the console logger version is because that was declared virtual, which triggers the runtime dispatch. So this is kind of a more interesting thing, because now what we've done is we have pulled out the client code, so that the client code now, unlike the previous case where the code that was doing the calling actually knew because it had just created a console logger. But in this case, we have a function, this client code function. It doesn't know the type that it's operating on. Doesn't need to. It just knows it's getting it by base class reference or pointer, so it knows that it is something derived from this class. And in this case, that the code calling the client code can pass in different loggers and get different behavior. So we're creating a new logger now. This is a file logger, and now our client code can call in either a console logger or a file logger, and the code is calling into our client code. The client code then has no knowledge of or care about what the actual type of the object is. And this is the power, that we've written all this code that simply says, give me a library, any library at all, as long as it follows this API, and I will behave properly. Do we follow what's going on there? All right. So we can have a number of different implementations, maybe a dialog box, maybe something going over the network. I want to talk about Barbara Liskov and Liskov substitution. She defined what she called the subtype requirement. And what she said is that if you have a subtype D, so D is a subtype of B, if the provable properties of objects of B are also the provable properties of objects of D. And in practice, the way we interpret this is that any code written against the B API will behave properly against the D API if it is a proper, with a D object, if it is a proper subtype. Now, the point I want to make is that not all subtypes, just because we have inheritance, that doesn't necessarily mean it is Liskov substitution. So here's my example. Here's surprise logger. I call it to log a message, and what happens? It's a surprise. So my point here is just that it fails to provide the semantics of log message. Now, why is this important? Because what I'm trying to say is just because you use derivation doesn't mean that it's really object-oriented programming. Object-oriented programming means that as we derive, we respect the requirements of what the base class states of the requirements of the API. So, so in our model, what we're going to be doing for object-oriented programming is, as implementers, it is our requirement to implement derived types that do respect this. And as clients, we are going to make the assumption that all the types do. And the reason is, if we can't make that assumption, we can't actually write code that we can reason about. We have to be able to say that there's a protocol both in the code and in the meaning of the API, and that protocol has to be respected by derived classes, or there's no point in us trying to reason about what the client is doing. So what Herb and Andre said in their book, C++ Coding Standard, is he said, after the base class guarantees the preconditions and postconditions of an operation, any derived class must respect these guarantees. An override can ask for less and provide more, but it must never require more nor promise less, because that would break the contract that was promised to calling code. So we're going to both understand that that's our requirement as implementers, but it is also the assumption that we can live with as clients using object-oriented programming, because if you don't do this, you can't reason about code at all. We can't go forward. It's not a viable way of programming. So I would like to go into the implementation of how this virtual dispatch works, but instead I'm going to refer you to Inbal Levy's Back to Basics talk on Thursday in the same time slot, because again, we're limited on time. So I want to get first on design best practices. And one of the things I want to say is early people using inheritance saw inheritance as this is a way to reduce code duplication. We're going to reuse existing code. I have this code that does this thing, and I need some code that does something pretty similar. And instead of just rewriting it all, I'm going to get some inheritance relationship. And at first, you're going to feel great because you saved some duplication of code. But if you don't follow the object-oriented programming guidelines that we're about to talk about, you're going to end up with this unmaintainable mess. So the starting point is to think about object-oriented programming as saying that public inheritance models is-a, meaning in our example that we gave earlier, all of our derived classes, we can say this is a logger. That's what this is. It is a logger. And then that relationship model, if it doesn't work, then you're not doing it right, and you're going to be sorry. So in this case, we have, I tried to find an example of breaking this. What is the contrary? Well, in this case, I said one of the things you might have is a derived class that isn't really logging. It has the same API, but what is it doing instead of logging? It just shows you the current state. The last message gets displayed. Now, what's wrong with that? That's pretty similar, right? But notice, when we're logging things, we expect to see that the log is going to have these things in order. So it's possible that the client, the caller, might have logged a particular message in 3 parts. Right? Here's this thing, and then here's this thing, and here's this thing. And it's intended to be seen as part of a log, and it makes sense only as part of a log. If you were to take just the most recent thing and show it by itself, it might not make sense. So I grant you, it's maybe not the strongest example, but what I'm trying to say is that we need to follow the abstraction that we've defined and said this is about logging. And the reason is, think about you as a client. I want to write something for logging. But I realize that some of the logging objects are actually display objects. So now I have to think in terms of what is the best way to get logging right and displaying right. See the problem? You might not be able to optimize code for both cases. And so that's why it's really, really important that we have an abstraction that's defined by the base and we respect that abstraction. Because otherwise the client is in a lost position of saying, well, I don't really know what it is I'm writing to. It might be one of these, in which case I should write it this way, but it might be one of these and then I should write it this way. So our guideline is use object-oriented programming to model an is-a relationship, not for code reuse. Or as Scott said, make sure public inheritance models is-a, and as Herb and Andre said, public inheritance is substitutability. Inherit not for reuse, but to be reused. So the next guideline is make non-leaf classes abstract. And this was Scott's recommendation in more effective C++. And here is what his motivating example was. He said, look, suppose we have these two objects, but the objects, although we know they're lizards, they're actually held by base class pointers. They're just pointers to animal. And so what are we doing in that last line? We are doing an assignment. Scott points out this is something that C programmers do all the time. We dereference a pointer and then treat that as that object. And so what we're doing is we are assigning what animal 2 points to into what animal 1 points to. Is this going to make us happy? Right. What's actually going to happen here? Slicing, that's right. So basically what's going to happen is that the animal part of our lizard class is in fact going to be assigned over the animal part of the other lizard class, but only the animal part, not the lizard part. Why is that? Why? Because of this lie that we tell the compiler. We're telling the compiler a lie. We're saying this is a pointer to an animal. Is it? No. Now that lie works for us because we understand the lie and we respect it and we program right, but we are actually lying. We're telling the compiler this is an animal. It's a pointer. I'm pointing to an animal, but I'm not pointing to an animal. I'm pointing to a lizard. And so Scott was trying to solve this problem. My take on this particular problem is, I don't care. He said that this will happen a lot for C programmers, but I'm saying no. Object-oriented programmers won't do that. Notice, here's another situation. This isn't slicing, but it's still a logic error. Why? Because we have the pointer, and we dereference it to get the animal, and we ask, what is the size of this? Is this going to give us the right answer? No. It's going to tell us how big's an animal, not how big's a lizard. And in fact, this happens all the time. And in object-oriented programming, we are lying to the compiler, but it works for us. And why? It's because in object-oriented programming, we always follow this rule. And the rule is we only dereference object-oriented base pointers to access base class members. Meaning it's either a data member in the base class, assuming it's public, probably not a good idea, or it is a function, either a non-virtual function or a virtual function, defined in the base class. And that's the only time we ever dereference a base class pointer. Because to do anything else is implying that the thing we're pointing at really is what we're pointing at, and it's not. It's the lie we tell. But it works for us. So Scott came up with a way of solving the problem of this assigning two base class pointers to each other, or base class pointer referenced objects. And as I said, I'm not really that excited about the solution that he came up with because I wasn't really that interested in the problem. But one of the parts of the solution, in order to solve the problem, he came up with a guideline that I think will make better hierarchies, and that gets me excited. I like design guidelines because, when I look at code, I pretty much can figure out this is good code, this is bad code. Designs, I'm always a little, that looks like a good design, but I can't tell you why. Right? If I have design guidelines, I get excited by design guidelines. So here's Scott's guideline. He says, make every class in your hierarchy either a base only or a leaf only. So what does he mean? So here's an example. We have a base class and it has some derived classes. And in any non-trivial situation, eventually the requirements are going to be, we're going to create a D3, which is exactly like D2, except this one little thing is a little bit different. Right? And if you're a clever engineer, you're going to recognize, hey, you know what we could do? We could just derive from D2 and put a little tweak in D3. Boom, I'm done. Go home. And I know you'll do that because I did that. And it's because I did that I learned why this guideline is so great. Because what's going to happen is eventually you're going to get some new requirements on D2. And then you're going to have this divergence of implementation. And you're going to be in this weird situation where the logic in D2 has to do one thing if you're not being derived from, but something else if you are being derived from. You do not want to go down that path, right? It will lead to bad hierarchies. So if you're going to follow Scott's rule, I should say also, this is a violation of one of Herb and Andre's really, really important rules, item number 5, which is give one entity one cohesive responsibility. The problem we have here is that D2 has 2 responsibilities. One is to be instantiated and to do whatever D2 needs to do, but also to define the base class for D3. And when we originally came up with that, those were the same things. That's why we did it. But over time, they will not be the same things. And now we have this bizarre situation where we're going to try to write code that has to deal with both cases. That's going to be really hard to reason about, really hard to document, and really hard to maintain. So what do we do instead? What we do instead is we simply take whatever's common between D2 and D3 and create a new base class with this commonality. And we're now following Scots Guideline, which says every object, every type is either a base only, or it is a concrete, something we're actually going to instantiate, right? Now, Scott did this because he wanted, I'm going to show you how this solves his inheritance problem. But I'm okay if we stop there. That's the important thing. This is a better hierarchy. This is going to lead to better hierarchies, more maintainable code in the long run. And again, I say that, I don't know in the lighting, I don't know if you can tell in the lighting, but I have some gray hair. I got that by doing this, right? Okay. All right. So here's Scott's actual solution. Make every step in your hierarchy either a base only or a leaf only. Step 2. For the bases, make them abstract. In other words, they're going to have at least one pure virtual function. What does that mean? That means that the compiler will never instantiate it. You have to derive from it and implement those pure virtual functions, or it will not, the compiler won't let you make one. And then he also said, let's make the assignment operators protected. Now, remember, that was his problem. He was trying to prevent assignment from pointed to objects. And then he said, okay, when you make your leaf class now, you have to implement all of those pure virtuals. You have to make it concrete. And then you can make the public assignment, the assignment operators, you can make those public now, because if you actually have a lizard, you want to be able to assign lizards to lizards if what you actually have is a lizard, not just a pointer to an animal. Right? Now, Scott didn't say the last one. The last one is to declare that class final. That's me. I added that. And the reason Scott didn't say it is because he wrote this for classic C++, and final was only in the language in C++11. But this is the spirit of what he said. Don't ever derive from this, because this is instantiable. And so the rule is you either instantiate it or you derive from it. You never do both. Because, again, going back to Herb and Andre's rule, item 5, we don't want 2 responsibilities for one thing. Okay? All right, so that's the make non-leaf classes abstract. So the last design guideline I'm going to give you is use the non-virtual interface idiom. It's called NVI. Scott talks about this in item 35. He just says, consider alternatives to virtual functions. Herb and Andre discuss it much more, and they say, consider making virtual functions non-public and public functions non-virtual. So let's dive into this. So here is the logger as I presented it first. It is not how I would actually recommend you do it. I would recommend you do the version below it. Now, I want to make it clear, this is a substitution. This isn't derived from it or something like it. I'm saying don't do the first one, do the second one. So what's the difference? Well, the difference is that I've taken the virtual function and I have made it private. And now I've made a public function that's non-virtual. And so I'm going to do some prep work, possibly, do some cleanup work, but the base class is the class that's responsible for calling the derived class. Now, because of the way I've written it, this is inline, and if those comments are never filled out, I'm going to generate the same code that I would have otherwise. It's going to call straight through. Why is this so important? Well, part of the reason it's important, that's just the definition of what we're doing. Part of the reason it's important is because of that pre and post functionality. You might want to do post-checking. You might want to do cleanup. There's a number of things you might want to do. You might just want to instrument it. You might want to have a place you say, hey, I want to set a breakpoint every time we're calling into one of the derived functions. This technique prevents a client from calling directly into an inherited class without ever going through the base class. The base class remains in charge. So it allows you to enforce those pre and post composition, pre and post conditions. It's also robust in the face of change. Suppose, not doing it this way, we decided later, oh, I do have to do something, I do have a precondition I have to check, or I have to put myself in a state, or there's something I need to do before calling a virtual function. If you ever do that, you either have to break callers or you have to break derived classes. Right? This is a more robust approach. But there's something else, and Scott didn't talk about this other one at all. Herb and Andre got it, and that is each interface can take its natural shape. And what do they mean by that? I'm going to tell you. I read Herb and Andre's argument for NVI. And one of the things they pointed out was how many libraries do this, and what a good idea it is, and okay, I'm willing to give it a try. And so, I was working on a particular thing at the time. I was designing a particular item, base class, and I said, okay, I'll follow it. And I didn't think, worst case, a little extra code gets written, not a big deal. And so this thing, it had a bunch of stuff, but it had 3 particular virtual functions. And so what I did was I made them all private, and then I had the public, I created a public non-virtual that called into them. And it's interesting to me, and this is why I'm such a big advocate of this, because something that hadn't occurred to me at all in the way I'd written it first became really obvious when I wrote it this way, and that's this. From the caller's point of view, 2 of those 3 functions would always be called immediately after each other. They were really the same logical function. Any caller that wanted to do the first one would immediately follow it up with the second. The reason they were separate functions is because overriders might want to be able to override this one versus this one, or do it in different ways. So I then changed my code so that I had only 2 APIs for the clients to call, because 2 of them needed to be together. But I still had the three overriding points for derived classes. And that's what Herb and Andre were saying when they said each interface can take its natural shape. So if you have a public virtual, it has 2 responsibilities. It has to define the calling interface, but it also has to define the inheritance interface. And what does that violate? It violates item 5. Give every item 1 responsibility. That's why I got excited about that. Okay. So use the non-virtual interface idiom. And again, what I want to say is there's a particular cool kid who I have a lot of respect for. He's really bright. But something he wrote recently, he was kind of, non-virtual interface. This is a younger person. So when I say cool kid, it might actually apply in his case. But I don't think he has the kind of object-oriented programming that experience, that he understands why this is so. I learned this because, as I said, I read what Herb and Andre said. I was not really convinced, but I was convinced enough to try it. And when I tried it, I said, wow, my classes, my class hierarchies, my APIs will be better for following this advice. That's what I like. All right, so this is our best practice guidelines. Use the is-a relationship for inheritance. Make non-leaf classes abstract. Use the non-virtual interface idiom. So now let's talk about some build things. So I'm going to introduce you to Chris. Chris is using this legacy framework, but he doesn't have access to the framework. He has access only to the derived classes and the clients that are calling into it. And Chris discovers this error in the base class, and it's in a non-virtual function. So Chris is saying, I really, really want to fix this problem. I can't modify the base class. Maybe I can do an override even though it's not virtual. But Chris is a little worried because I'm not sure that I can actually get away with that. So Chris writes a test so that they can verify, right? Okay. All right, so here's our base with this erroneous, it's returning 0 instead of what Chris feels probably should be returning 1. So in the derived class, we are going to implement an override of erroneous, but we have to test it. So we're going to call test erroneous and make sure that that actually works to give us the right answer. So is this test going to pass? course it is, right, because why? Because we've created a derived object and we're calling a function on that derived object, and the compiler is going to get the right function there, even though it's not virtual. Is it a successful fix? No. What is the test that Chris should have written? Well, the test that Chris should have written was to use object-oriented programming. In other words, make the object, but hold it with a base class pointer or reference, and then call against the base class pointer or reference. Is this test going to pass? No. Why? Because, of course, the compiler is going to call the base class version, not the derived class version. Does everybody see why? If you don't see why, go to Inbals, and she's going to talk more about dispatch. All right. So is the fix successful? No. So the guideline is overridden functions must be declared virtual. All right. So in this case, I have my base class of logger, and what have I done? I took out the virtual destructor. Don't be doing that. All right, but that's what I did. Took out the virtual. Now, I've derived from it, and notice this particular class happens to have a data member, right? It has some state. Okay? Now, how do we use this? Well, we're going to create a new file logger, and then we're going to use it, and then we're going to destroy it by calling delete on the pointer, the base class pointer, which is what we do in object-oriented programming. This is perfect object-oriented programming. But what's really going to happen? Which destructor is going to be called? What? The base class, the logger, right? And because it's not virtual, it's not going to call the derived class. So what's going to happen to the state, to the data members of the derived class? They're not going to get cleaned up. That destructor is not called. Right? Now, of course, if there aren't any data members in the derived class, then it's safe, right? No, it doesn't work that way. The standard says it is undefined behavior to delete a derived class object with a base class pointer if the destructor is not virtual. So what we need to say is always make base class destructors virtual. All right. So in this situation, I'm recommending that any virtual function that you have in your code base, you declare it virtual. I like that. I think it's good. It's my recommendation to you. But notice, it's virtual. The function is virtual if it's a derived, if it's an override of a virtual function. Then the function is virtual whether you say it's virtual or not. The virtual keyword there is optional. I recommend it, but it's optional. So let's take a look at this. This doesn't have a virtual keyword for this. Is it virtual? False. Why? It doesn't need one, does it? Log message is not an override because when you weren't looking, I took out the const. Okay, so the point is, this is a really easy mistake to make. I've made it, no question. It's a really easy mistake to make. So how do we fix this? Well, it turns out there's a keyword for that. It's a modern keyword. It's introduced in C++11. And if you declare a function to be an override, and it is not, for any reason, in this case because we didn't exactly match the signature, so we didn't override, you will get an error. So override has two really nice functions for us. It informs users of your intent, but it also has the compiler verify at compile time that you are in fact overriding. That will catch bugs that are hard to figure out and that will waste your time. So this is a great thing. So absolutely, if it is an override, declare it as an override. Telling other people reading the code, and when I say other people reading the code, who do I mean? I mean you in 4 months when you've forgotten what you were doing, right? Am I wrong about that? Okay. All right. So use override for overridden functions. Now I want to talk a little bit about something. This is C and C++. It's classic. If we declare two things in different scopes, an inner scope and an outer scope, that have exactly the same name, is that going to compile? Completely legal? Well defined what exactly it means. It is not an error to declare something in the inner scope. However, any code in the inner scope that uses that identifier is going to refer to the inner scope version as opposed to the outer scope version, right? And notice that's true regardless of whatever the type is. So in this case, I also want to point out that when we're talking about scopes, it could be a type inside another type and type inside a namespace. Also, a derived type is considered to be inner of its base. And if you think about that, it's really important because when I'm writing derived code, I want to be able to refer to base objects. And so that's what it does. So any derived class If you declare a new type in the derived class, you've automatically hidden any base declarations of the same name. And that's true even if it's a different type. So in this case, I have a type alias that says that x is a type, x is an int. But in the derived class, I actually instantiate a particular object with the name x. Now, down below, I try to make vector. Vector requires that I tell it the type, and x, I think of it as a type. In the base class, we said what the type is, but in fact, the compiler is going to look at that x and not see the base, because it's not going to look there. It's going to look in the derived class. Okay? Does everybody see why that won't compile? All right. All right, so the overloading rules for functions are a little more complicated now. Because everything we've been talking about so far, we have types or objects. There can only be one with a certain name. But for functions, you can have multiple functions that all have the same name, and that's where we have overloading, and the compiler just figures out what the right thing is. So the rules for function overloading, and the first thing I have to say is this is very, very much a simplification. Right? These are very complicated rules. But essentially, what we do is we look for the name in the call scope. If we find it, we find all the instances of that name. Remember, overloading happens so there can be multiple things with that name. And then we stop looking. If we don't find it, then we move to the next outer scope, and we start looking there. So again, this is simplified. It can be complicated for some cases. But here we have a base class that has foo, and a derived class, the base class foo takes an int. The derived class foo takes both a long and a double. And now, in our derived class constructor, we actually call foo with an integer, with a long, and with a double. Everybody see what we're doing? Okay, what's the output? Okay, what's the output? False. Why? Well, the call is ambiguous, right? Because integer could call long, could call double, and it will not call int because the int foo is hidden. Does everybody get the idea of what's going on here? Okay. What if we made it virtual? Would that fix it? No. Yeah?
How is the int foo hidden?
The int foo is hidden because base is an outer scope, derived is an inner scope. We declared foo in the outer scope, and we declared it in the inner scope. When we call foo, it's going to look in that inner scope. If it finds it, it's going to collect all the foos in the inner scope and stop looking. That's the rule, which is a surprise, but that is the rule, right? Essentially, this issue is going to come up when people try to mix overloading and overwriting. It's almost certainly not going to make you happy. So do one or the other, but don't do both. Okay? All right, so don't mix overloading and overwriting, or as Scott says, avoid hiding inherited names. So Chris is back. Chris, again, using a legacy framework, doesn't have access to the framework code. And Chris now overrides a virtual function with a default parameter. Chris thinks that the default parameter in the base class framework is kind of ill-chosen. It's not a good default parameter. And so Chris, in the override, gives a new default, but isn't really sure that's going to work. So Chris, again, writes a test. So here's our base. This function has a bad default value of 0. Really, Chris thinks it should be 1 instead of 0. So then Chris writes a test bad value, and checks that the right value is being passed in. So creates a derived object and calls test bad value. So again, is this test going to pass? Yes. Is it a fix? No. How should Chris have written it? Chris should have written it this way, using object-oriented programming. We're actually going to call the base class. Now, is the test going to pass? No, because the compiler generates the code to call the function at compile time. And at compile time, the compiler realizes that it needs to pass in a default parameter because a parameter is not provided. So the compiler has to provide it. And the compiler is going to provide the parameter specified in the signature. And when the compiler is generating this code, it doesn't know what the derived class is. Couldn't possibly use that one. It's going to use the base class, right? So the fix is not successful. So the issue now is, should we ever have a derived class with a default that's different? I think it's going to be confusing if the default is different. But what if you said, well, wait a minute, I want to make it clear, so I'll make the default the same. If it says default 50 in the base, I'll say default 50 in the derived. I would encourage you not to do that. That's a DRY violation. What is DRY? Say that again.
Don't repeat yourself.
One more time.
Don't repeat yourself.
So he's playing it on me now. He would have gone forever. All right. Yes. The problem is if we do that, then we have a maintenance problem if the default is ever changed in the base, right? So don't do that. And from the implementation's point of view, it doesn't matter what the default is. The implementation is simply going to get a parameter and has to do the right thing regardless of what the parameter is. All right, so don't specify default values on function overloads. All right, so in this case, what we have is, I think I changed the slide and it's going to be a mess. All right. So in this case, what we've done is assume that this is actually a file logger and not a console logger in there. So we have created, one of the things that we want to be able to log is a constructor. So inside the constructor, is the fact that we have created a logger. So inside the constructor of the logger, we log that the logger has been created. So what's going to happen down here? What's going to happen down here when we instantiate CL? What is the type of the CL when we call the base class constructor? What is the type of the object? It's a logger. It's not the derived class, whether it's supposed to be console or file. I apologize for that change that happened. But the point is that during a constructor, the type of the object being destructed is the type that's being destructed. It is not the derived type. So if we call a virtual function, the correct function to call is the base function, or whatever that object is, not some derived function. Now, you may find that really annoying because you actually wanted to do something based on what the thing is going to be eventually. But notice the issue here. When a type's constructor or destructor is executing, the type of that, both the static and the dynamic type of that object, is the type that's being constructed or destructed, not the derived. It becomes the derived when the base is finished constructing, or at least the next on the inheritance chain. So virtual function calls will not resolve to the function's derived type. This is actually a good thing, even though it might be frustrating to you. And the reason it's a good thing is because, remember, we construct the base first and then we construct the derived. And the construction of the derived is where we're going to construct the data members of the derived. And that's why I changed it from a console example to a file example, but I didn't quite change it properly. Because I wanted to point out that if you were to call, if the call actually called the derived class log message, you'd be logging to the file logger which hadn't opened the file yet. You'd be writing to a stream that hadn't been initialized. And that's unlikely to make us happy in the long run. So it's actually a protection that when you are in the base class, any virtual calls you make are going to be against the base class, not against the derived class. Does that make sense? It's a bit of a surprise, but when we think it through, we realize, no, it's for our best. It's in our best interest, and it's what we want to do. So both Scott and Herb and Andre recommend this. Don't call virtual functions in constructors or destructors. So now we have the situation where in this application that we're building, where we want to be able to do logging, it turns out that there's actually a way that we can, the requests from different support departments are, if you're logging code that is for us, we want to be messaged for that. So we have an SMS logger, right? And so the API for the SMS logger is that you have to set the phone number before doing the logging so that the SMS code will call the right department's IT standby people. Does that make sense? You see what we're trying to do here? So if we're logging against, if we're doing stuff where the accounting department needs to know, then the IT part that does the accounting software is going to be notified if it's something else. All right. So how do we do this? Well, in the application code, with our logger, when we get into a new area of the code and we want to say, oh, now we want to notify someone else, we just have to call setCaller with whatever the correct phone number is for that. And of course, as you see, it's not working. Why is it not working? Because the compiler sees logger as what type? It's a pointer to a logger, and the logger API doesn't know anything about setting the phone number. So, well, the solution to not compiling, of course, is always just to do a cast, right? So everybody knows that. You've been writing C++ long enough to know that the solution to every compile problem is you just put a cast in until it works, right? Okay, well, this works. This is going to compile now. So we're ready to ship it, right? What's the problem here? That's right. That's right. We are telling the compiler, ignore the fact that you think it's a logger and assume that it really is. I'm telling you it's an SMS logger. All right. So when we draw inheritance hierarchies by tradition, by common practice, we draw the base class at the top and we draw the derived classes below. And so when we talk about an upcast, what we're saying is I have a pointer or a reference to a derived class, and I'm going to treat it, I'm going to cast it to a pointer or reference to the base. Is that going to be safe? Yes. In fact, that is, as I've been saying, that's object-oriented programming right there. We have a pointer or reference to a base when it's really a derived. Absolutely safe. Do it all the time. Completely works. And the reason it works is because of Liskov substitutability, right? We have a derived. We can always substitute. Okay. But what's a downcast? Well, a downcast is when you have a reference or pointer to a base class and you cast it down the hierarchy, meaning you're now saying it is actually a derived object. That, not so safe, right? So what do we do instead? So one option is what we just did, this unconditional static cast. This is the most efficient thing to do, and we're all C++ programmers, so we like doing efficient things. It immediately works. It's efficient, it's effective, but the compiler can't verify what you're doing. You better know what you're doing. It better be true. And maybe sometimes it is. Maybe you say, well, in this part of the code, we'll only get here if we're using an SMS logger. Okay, maybe. If there's code maintenance that happens in the future and you get there in some other way, bad things will happen. Right? So a better option is to use a conditional or dynamic cast. And the way this works is the compiler actually generates code which checks at runtime to make certain that the actual object is what you're saying I want to make a pointer to. And that is safe. There is runtime overhead because this verification has to happen. And the other thing is we have to code for the possibility of a failure. Because remember, it might not be that thing. So it's a little harder to code because we have to code both options. So here's how we would do this. I'm doing a dynamic cast to an SMS pointer of whatever, or SMS logger of our logger. So because the dynamic cast may fail, how would it fail? Well, the way it fails is that it's going to return a pointer to null instead of a pointer to an SMS. Right? Or I should say a null pointer. The type is still a pointer to an SMS, but it's null. So that means we have to write code that checks for that. Now, we can also use static cast to cast references instead of pointers. And a reference can never be null, so we don't have to check. Right? Well, we don't have to check, but we have to catch because instead of returning a null pointer, it throws an exception. Right? And either one of these is perfectly fine. It's just you have to write failure code in either case. You have to write it in the catch block, or you have to check for null. Either way, you have to make the decision about what that is. All right. So I want to say that that's a better option than the static cast. But there is yet a better option, although it's not necessarily mechanical. You can't just say, oh, use this thing. You have to think about what it is we're trying to accomplish. And we have to think about what we're trying to accomplish with the derived class by looking at the base class and say, what is it the base class, in terms of the base class makes sense, what is it that we're actually trying to do? So in this example, what I said is, well, imagine that the base class, as part of the logger, you could set the department info before you start logging. That's a new API to loggers. Not only can you log a message, but before logging the message, you can say, by the way, I'm about to log a message that is interested to this department. I'm not talking about phone numbers or anything. I'm just saying this is the department. Now, all the other derived classes don't need to override at all. The default behavior is to do nothing. But the SMS logger can, in fact, override that to look up the on-call phone number for that department and call its own set caller. So what happens then in the app code you just say set department info for whatever the current department is you're about to do logging for, and all loggers do exactly the right thing. Right? So this avoids the cast. It's better, easier to understand. It's safer, and I think easier to document, easier to reason about. Yeah?
In that case, would you make set call the private member of the class?
You could, it depends on what other situations you might want to use this class in. You could make an argument for either way. That's outside of any point I want to make in this class. I think you could logically do either way. All right. So, what did I do? Okay. What Scott said was minimize casting. What I say is use dynamic rather than static for downcasting, but avoid casting by refactoring where possible. And you may not be able to control the base class. It may not be your base class, so it may not be possible. Generally speaking, I would say that anytime I see a dynamic cast, I look at that and say there's a failure here. Now the failure may just be that, well, we can't change the base class, we're locked into that, so this is what we're doing. But a better design almost always could theoretically replace any dynamic cast. Okay? All right, so this is my best practice for build. Overridden functions must be declared virtual. Always make base class destructors virtual. Use override when overriding functions. Do not mix overloading and overriding. Don't specify default values on function overrides. Don't call virtual functions in constructors or destructors, and use dynamic rather than static cast for downcasting, but avoid casting altogether. It's a casting by refactoring where possible. And going back and talking about the design, these are the things that I get more excited about. I think these are better, more fun. Model is in your public inheritance. Make non-leaf classes abstract, and use the non-virtual interface idiom. So that's my idea of best practices in object-oriented that will fit in an hour and still have almost 8 minutes for questions. Thank you. Are there any questions?
So
I have a question for you. Oh, I'm sorry. Go ahead.
So in your example with the SMS Logger, the class that's using that logger expects it to be an SMS Logger. And so isn't there a way of maybe building or constructing this class, giving it a reference to an actual SMS Logger instead of a generic logger, and re-architecture your code so that that's the derived class it's expecting and not the base class?
Okay, let me explain what the case is. The case in this situation is that we're writing code and we don't know that it's an SMS logger. So that's why we have a log pointer, because it could be any logger. The calling code could give us a different, the client code, which is passed in a logger, doesn't know what the type is, does whatever it's going to do, logging things as it goes. If you happen to have a certain part of your application where you know the SMS logger is the only kind of logger I would ever use in this situation, then I wouldn't pass in a pointer to a logger. It's not object-oriented programming at that point. Just pass in an SMS logger and use it. And in that case, we might not want to make the set phone number to be private, because you may want may want the client to be able to set the phone number directly. That might be an argument for making it public. It all depends on how you intend it to be used. Does that make sense?
I actually have 2 questions for you.
Oh, I'm sorry, that's over quota.
First one, are you in the standards committee?
I do go to standards meetings, but I am not a regular of standards meetings.
Okay, the second question is, with regards to virtual base class destructors, if it always has to be virtual, why doesn't the standard change it and say that the compiler makes it virtual?
Because it doesn't always have to be virtual.
But the behavior is undefined if it's not.
No. You may promise never to destroy the class from the point of view of the parent.
So let me take a stab at explaining this. when you define that base class, it may in fact, the compiler doesn't know what you might do in some other code somewhere else. So you might derive from it, or you might not derive from it.
Well, if it has at least one virtual function.
I would argue that if it has at least one virtual function, it probably would be safer for the language if destructors were.
Yes, that's what I meant, forgot to mention.
Yeah. But there are use cases where you could say, we only create these objects through a factory and we dispose of them in a certain way. And we know when we dispose of them what the actual type is. And we don't need the overhead of having a virtual function there. So I think that was probably a more interesting use case for people when it was originally developed than it would be today. I think today people would opt more for safety than that kind of narrow use case. But that's not the decision that was made then. Could you make an argument that it should be changed now? Is there code that would break? Probably there is code that would maybe not break, but be a little less efficient. I don't know that anybody feels the pain enough to go through the process. But I don't think it would meet a lot of resistance. I think a lot of people would say, yeah, that probably makes sense. It probably makes safer code.
Thank you.
Hi. In cases of interface segregation, and you have a reference to an object through a pointer to one of the interfaces, then do you have any advice on casting between interfaces?
So can you tell me what you mean by interface segregation? Are you
So
talking about multiple inheritance?
yes.
Okay, so now that I think I understand better, ask me the question again.
So in the maybe in an example similar to what you showed, instead of introducing a new function in the logger interface class, you make a separate interface to set the callee or whatever you want to achieve, right? And
So you're suggesting that maybe instead of deriving only from logger, we could have an SMS logger that derives from logger and also derives from something else that has that set callee. I'm not certain that it makes much difference in this case because the code we were talking about only has a logger pointer and expects it to be a logger. If you have an object that needs additional API, it really doesn't matter how that additional API got there. You could define it in the derived class, you could inherit from something else, but the end result is what I talked about, which is that you're going to have to somehow figure out that it's the right thing, and I recommend you either use dynamic cast or refactor it so that you're doing something in the base class that makes sense and the derived class does the right thing. I don't think that multiple inheritance changes it complicates some things, but it doesn't change the overall picture of anything in that case.
Okay.
Hi.
Hey, I was wondering about one thing. You were suggesting that we make leaf classes and class hierarchies final. The core guidelines actually recommend the opposite, that we should not set leaf classes or classes in general as final if we can avoid it. I was wondering if you could comment on that.
So the cool kids don't want you using final, and the reason is the cool kids play cool things where they try to do things with templates where they have a class and they decide, well, there's this basic class, empty base class optimization they can use if instead of including this object, we actually derive from it. And if it's final, of course, they can't derive from it. First of all, that's almost certainly, none of those techniques are going to make sense in an object-oriented world because they don't know what the type is at compile time. So just, those things probably aren't going to work if you're using object-oriented programming. So that's the first thing I would say. The second thing is that I believe in 20, we now have a way of not having to use the empty base class optimization. But it's no question that the cool kids are saying, don't use final. But I'm saying, if you're doing object-oriented programming and it's a leaf class, I don't think the arguments for why you shouldn't use final, I don't think they apply.
All right, thanks.
Okay. All right, well, I think we're there. I really appreciate you coming here. There were a lot of great talks going on at this time. and this is not the sexy topic. But I do appreciate your spending time with us today. Thank you very much.